recorded. Okay. All right. All right. Couple of things here before the start of the lab today. Okay. And start kind of lecture today. Okay. So for this week lab. Okay. So we will use the RootWeb quite intensely. Okay. So you need to use RootWeb twice. Okay. So in this case, if you don't remember how to operate RootWeb, okay, please review the video. Okay. So I already posted one video on the CH327 EDCAT. Okay. And the second thing is kind of when you weigh the chemicals, okay, the two chemical alpha, the styrene, okay, and also the NBS, okay, so make sure you weigh exactly the mass, okay, so the alpha, styrene kind of 0.5 gram, okay, and then the NBS kind of 0.77, 0.788 gram, okay, so make sure you weigh exactly the amount, okay, because there's a no purification step, okay, so that means if you any of this using excess, okay, will showed up in kind of final product, okay, so make sure you weigh exactly the amount, okay, right. All right, again, if you have any question, you just type in the chart window, okay, all right. Okay, so let's continue chapter 11, okay. So last time we talked about kind of the mechanism 1, okay. Mechanism 1, okay, so you add the electron file first, okay, generally kind of the carbon cation, okay. So carbon cation kind of planar structures, okay, and then nucleophile coming, okay. So under mechanism 1, okay, so the first reaction we learned is kind of addition of the hydrogen halide, okay. So pretty much the HX, okay, so one the carbon pick up the H, okay, another carbon pick up the hydrogen, okay, chloride, bromide, iodide, or the fluoride, okay. And so there's the one tricky thing about this reaction, okay. So if it's kind of symmetrical reaction, okay, the symmetrical kind of alkene, okay, so the both carbon same, okay, so it doesn't matter which carbon pick up the hydrogen, which carbon pick up kind of hydrogens, okay. But if it's kind of unsymmetrical alkene, okay, so for example, show this one, okay, so that's the propene, okay, so and then if you react with kind of HCl, okay, so there are kind of two possible products, okay. Yeah, so if you have the question about the pre-lab and also the homework, okay, so come to my office hour, okay, so there's kind of office hour, tomorrow, okay, so also the maybe later today, okay, so okay. All right, okay, so for this kind of unsymmetrical alkene, okay, so there are kind of two possible products, okay. One is kind of the terminal carbon, okay, so terminal carbon pick up okay, so you can stay here, okay, so after the lecture is done, okay, if someone needs some urgent help, okay, All right, okay, so one kind of the product kind of the theta bond, the terminal carbon pick up hydrogen, internal carbon pick up kind of chloride, okay. Another kind of reversible, okay, so the terminal carbon pick up chloride and then internal carbon pick up hydrogen, okay. So if there's no residual selectivity, okay, so you should get a 1-to-1 ratio of these two, okay. But for the reality, okay, we only get one the major product, okay, so that's the terminal carbon, okay, so the carbon with more hydrogen pick up hydrogen and then internal carbon pick up the chloride, okay. Right, so that's kind of one of the most important kind of the residual selectivity kind of rules for the organic chemistry, okay, called kind of Markov-Nikod's rule, okay. So when you add kind of HX to the alkene, okay, hydrogen also add carbon with more hydrogen attached, okay, and then the hydrogen, okay, goes kind of carbon with less hydrogen attached, okay. So for example, this one, okay, so the terminal carbon has two hydrogen, okay, and then you add another hydrogen on it, okay, so that's the hydrogen goes kind of carbon with more hydrogen attached, okay, and then the chloride goes kind of the internal carbon with less hydrogen attached, okay. And here's kind of very important, okay, so easy to remember it, okay, so that's I already told my student kind of you can remember this one as kind of rich get richer, okay. Richer, okay. Right. So what's that mean, okay, so if you reach in the electrons, reach with kind of hydrogens, okay, and then you get more hydrogen after the addition reaction, okay, get richer, okay. Right. Okay, and then here's another example, okay, and so we have this the alkene, okay, so this terminal carbon has kind of two hydrogen, and then this internal carbon has two methyl group, okay. When you addition kind of the HBr, okay, And then yeah, the rich got richer, okay. So yeah, the terminal carbon pick up hydrogen and the internal carbon pick up yeah, the bromide, okay. Right, someone asked kind of why is that, okay? So that's kind of the stability of the carbon cation. Remember for magnesium one, okay. So we generally kind of carbon cation as intermediate, okay, and so just use this one as example, okay. Yeah, for this arcane, okay, and then when we add kind of the hydrogen, okay, so generally kind of the carbon cation case. Remember, yeah, that's always first step with that do it, okay. So why is kind of you open the double bond like this way, okay, open like this, okay. So this carbon kind of lose electrons, okay, and then pick up the another carbon pick up hydrogen, okay. And then you can generate kind of the carbon cation like this, okay. Right, so the internal carbon pick up hydrogen. Right. Another way is kind of you open your C double bond like this. Yeah, that's right. Okay, so yeah, rich got richer also means kind of hydrogen goes kind of more substitute carbon. Yeah, rich got richer means kind of the more hydrogen, you get kind of more hydrogen. Okay, so yeah. Right. Okay, so open like this way, okay, and then yeah, internal carbon pick up the hydrogen. Okay, like kind of internal carbon yeah the terminal carbon pick up the hydrogen. Okay. Right. Okay, so then you find kind of this is kind of if we the internal carbon pick up hydrogen, we generate kind of the primary carbon cation, okay. And if you kind of this carbon pick up hydrogen, okay, and generate kind of the actually kind of this should be tertiary carbon cation, okay. Right. So you see kind of two different kind of the carbon cation, okay, and then the definitely kind of tertiary is the most stable, okay. So that's why the pathway like to kind of go this way, okay. So that's the right way, okay, and then eventually kind of the bromide goes kind of the internal carbon, okay, also more substitute carbon. Yeah, so that's the reason for that, okay. And so that's the stability of the carbon cation, okay, and then give you guys kind of a couple more example, okay. Right. Right. So we have this arcane, okay. So arcane addition kind of pretty easy, okay. Just one carbon pick up something, another carbon pick up another thing, okay. But the important thing kind of which carbon pick up which, okay. Right. So for this one, okay, so remember kind of we follow kind of Markov-Nikolov rule, okay. So we also call kind of Markov rule, okay. And then the bromide will go here, and then hydrogen will go here, okay. So because there are kind of two carbons, okay, here, okay. And then this carbon already has one hydrogen, okay. So the Markov-Nikolov rule, okay. And the carbon with more hydrogen attached, okay, and get here another carbon, okay, another hydrogen, okay. Yeah, so here, okay. That's your rich got richer, okay. All right, okay. So now actually kind of you guys take a try, okay. Yeah, try this question and then also try this one. Yeah. All right, so determine where the hydrogen goes, where the bromide goes, okay. Which carbon pick up hydrogen, which carbon pick up bromide. Yeah, draw the product. So pretty much you need to just find the follow Markov-Nikolov, okay. So the carbon with more the hydrogen attached, okay, get hydrogen, okay, another carbon get kind of here the chloride or bromide, okay. All right, okay. So can anyone tell me kind of which carbon pick up hydrogen, the top carbon or kind of bottom carbon? Okay, type in the chart window. Okay, top carbon pick up hydrogen or bottom carbon pick up hydrogen? Yeah, looks right. Right, top. Okay, because the top carbon has 2 hydrogen already. Okay, yeah, rich got richer. Okay. Right, and then yeah, when you draw it, kind of you don't need to show the hydrogen. Okay, you can just directly show the kind of chloride. Okay, so at the bottom carbon, that should be fine. Okay. All right. Okay. So now we come to hard one. Okay. So can anyone tell me kind of the which the carbon pick up hydrogen? Okay, left carbon or right carbon? This is the hard one. All right. Okay. So looks like all you guys kind of provide the right answer. Okay. So pretty smart. Okay. All right, so for this question, okay, so although, okay, so yeah, for both, yeah, the carbon, okay, so yeah, both this carbon has 1 hydrogen, okay, looks like cannot apply kind of Markov-Nikodym group, but yeah, remember the fundamental for yeah, that's right, benzoic, okay, fundamental for the Markov-Nikodym group kind of stability of your carbon cation, okay, so if it's kind of yeah, right carbon pick up hydrogen, okay, you generally kind of something like this, okay. So this is kind of benzoic kind of the carbon cation, okay. That's kind of extremely stable, okay. So we learn kind of substitution chapters, okay. Also elimination chapter, okay. And preferred, okay. So if you have this carbon pick up hydrogen, okay, so you generally kind of just regular kind of secondary kind of carbon cation, okay. So yeah, that's not as stable as kind of benzoic. Reason for that kind of this positive charge can delocalize into kind of benzene ring case, kind of spread out, okay, more stable, okay. In this case, the final product should like this, okay. All right, okay, and then yeah, so remember, like I said, like last time, okay, so yeah, this reaction generally kind of carbon cation, okay, so the one big problem kind of rearranged for the carbon cation kind of and one example showed here, okay, so yeah, we have this the alkene try to add the HCl on it, okay, and then theoretically speaking, kind of we should get this as a major product, okay, so yeah, the hydrogen goes kind of terminal carbon, and then Cl goes kind of internal kind of carbon, okay, but yeah, reality we also get this one, okay. Reason for that kind of we have kind of 1,2 hydride shaped, okay. There's 1 hydrogen on this quaternary tertiary carbon, okay, shaped to this carbon, okay, and then you generate the more stable the tertiary carbon cation, and then chloride goes here, okay. All right, and then for the rearrangement, okay, give you guys kind of another example, okay. So I will show you what's other definition? Oh. So other probably just I guess, okay, so some kind of maybe some kind of elimination product, okay, or some kind of so maybe kind of general kind of the conjugated elimination, okay, so that's I guess, okay, so yeah. All right, okay, so now give you guys kind of another example, okay, so yeah, that's the 1,2 RQ shift, okay. All right, so we have this one, okay. And theoretically speaking, okay, we should get kind of this as a product, okay. And hydrogen gold kind of terminal carbon, okay. So that's a theoretically speaking, okay. But for the reality case, so major products like this. Right. Okay, so what happened kind of just quickly draw the mechanism, okay. So yeah, it's bound to pick up the hydrogen, okay. Yeah, the hydrogen's here. You generate kind of the carbon cation, okay. So it looks like a secondary carbon cation, okay. Secondary carbon cation next to quaternary carbon, okay. So you can have kind of 1,2 RQ shaped, okay. And then generally kind of more stable the tertiary carbon cation, okay. So the hydrogen still here, okay. And then the chloride come in, okay. Give you this product, okay. Okay, so just a little bit careful about carbon cation kind of rearrangement, okay. Right. And then second kind of issue always kind of about the stereochemistry, okay. And for the mechanism one, okay, because we generally kind of the planar carbon cation intermediate, okay. So the nucleophile can either go from top or go from bottom, okay. So that's can have kind of both the anti-addition or syn addition, okay. So that's some kind of concept kind of we need to learn about the stereochemistry of the addition reaction, okay. So what's the syn addition, okay? So syn addition, what happens kind of the nucleophile and also electron add on same the side of the carbon double bond, okay. Right. So pretty much into BDL. Right, nucleophile and then electron file, okay, go the same side, okay, and eventually you generate kind of that's what we call kind of the syn addition product, okay. So maybe draw like this. Yeah, so that's a syn addition, okay. So anti-addition is kind of the nucleophile and those the electron file at opposite side of the theta bond, okay. Right. So one go from the top of double bond, another from the bottom of double bond, okay. And after reaction, okay, so generate something like this, okay. Yeah. So that's the anti-addition, syn addition, okay. And for mechanism one, okay, so that's the relatively easy, okay. So just because the carbon cation, okay, so you can nucleophile come from top or from bottom, okay, doesn't matter, okay. So you generate kind of both, okay. And so that's in another words, okay. So mechanism one has no stereochemistry, okay, has no stereochemistry, okay. And then in this case, quite often happen kind of when you draw the kind of the product of mechanism one, okay, so sometimes kind of you just draw the straight line, okay, sometimes kind of probably for the smart work, okay, file, okay, so you have to show the both enantiomer, okay. All right, so for example, we have this one, okay. So theoretically speaking, kind of because the hydrogen goes here and the chloride goes here, okay. And then because the chloride can go either the directions, okay. So you show that should be fine, okay. But for the smart work file, okay, so probably you need to show both, okay. So enantiomers, okay, plus okay, for both, okay. And so that's for the asymmetrical kind of arcing, okay. So if we do the addition to the symmetrical arcing, okay, like this one. So because this time there's also no residual chemistry, okay. So here it's kind of there's a residual selectivity for Markov-Nikodym flow, okay. But here even there's no residual chemistry, okay. So in this case you can generate kind of all four possible kind of product, okay. R, S, S, R, kind of, and also kind of S, S, and R, okay. So I'm gonna quickly draw you all four, okay. Right. So these pairs kind of from syn addition, okay. So HCl, okay, at the same side of the bond, okay. Right. Another pair is kind of the anti-addition, okay. Yeah. So totally all four possible products, okay. And if you like, you can design RNS, okay. So you can find kind of you find kind of the SSR, okay, RSSR, okay. So all the four kind of possible products, okay. And then actually kind of the two pairs of enantiomer, okay. So this pair of one pair enantiomer is this pair kind of another pair of enantiomer, okay. All right, okay, so that's the first reaction, okay, so the under the mechanism one, okay. A second reaction kind of addition of the actually kind of the addition of the halide to alkyne, okay. So not kind of alkene, okay, alkyne, okay. So for addition of alkyne, okay, so a regional chemistry still follow kind of Markov-Nikolov rule, okay. Yeah, so really depends on how many kind of equivalent of the HX, okay. So you can add one pair, okay. So if you control only one equivalent, okay, showed here, okay. So that's alkyne, okay. And then you add kind of one equivalent kind of the HCl, okay. So you see kind of still follow Markov-Nikolov, okay. So the hydrogen goes kind of carbon with more hydrogen attached, that's the terminal carbon, and then chloride goes kind of internal one, okay. And so if you add two equal or excess of the HX, okay, so that's kind of add just the both pair of HX onto kind of the alkyne, okay, get kind of the dihalide, okay. So also we call kind of the germinal dihalide, okay. So germinal means kind of the both halide onto the same carbon, okay. So the reason for that kind of still Markov-Nikolov rule, okay. So you want to get kind of the add one pair, you generate kind of the internal carbon has kind of a hydrogen, okay, and then terminal carbon has hydrogen, and then add another pair also for Markov-Nikolov, okay. So that's should be kind of pretty straightforward, okay. So just quickly give you guys kind of another example, okay. Addition of the halide, okay. Addition halide to kind of alkyne, okay. Right. Both the Cl goes kind of internal carbon, okay. So we just call kind of germinal dichloride, okay, for this case, okay. All right, the second reaction, okay. All right, and then we move to the third reaction, kind of addition of water, okay. So for additional water, okay, so there's kind of special name called kind of acid, the catalyzed kind of the hydration, okay. So for the water, okay, so pretty much kind of weak nucleophile, weak base, okay, water, okay, so cannot kind of directly add to the CC bond, okay. So you have to give a little bit help, okay. So we use kind of some strong acid, okay, and then convert the add the hydrogen to kind of the bond first, okay, then kind of the okay. So maybe show you guys what's going on, okay. So this is the acid catalyzed hydration, okay. All right. So pretty much you have kind of alkene, okay, and then pick up the hydrogen, okay, protons, okay. Right, then kind of carbon cation, and then falling kind of the water can come in, okay. Yeah, if there's no such help, okay, so the water cannot open the CC bond, okay. Right, because the water is kind of neutral nucleophile, you have to do one more step, okay, remove the one hydrogen from kind of the water, okay. So right. So normally some kind of another water coming, okay, pick up this hydrogen and then shift back, give it kind of final the alcohol, okay. So right. So you can see for the overall process, okay, okay. So you lose one hydrogen, okay, protons, okay. So at the very beginning, okay, acid, okay, and then eventually you gain one the hydrogens, okay, protons, okay. So that's that's why the acid kind of catalyst, okay. So recycle it, okay. Right, okay, so if you guys still remember some reaction we learned in chapter 10, okay, someone maybe quickly realize, okay, so this process actually kind of reverse process of the acid catalyzed kind of dehydration, okay. So in the chapter chapter 10, okay, so we are under the elimination product, okay, so yeah, the elimination reaction, okay, the third reaction, okay, so yeah, acid catalyzed kind of the dehydration reactions, okay. So last year we have some kind of alcohol, yeah, we lose one pair, yeah, one kind of water, okay, and we get kind of alkene, okay. Some people guys kind of get confused, okay, so yeah, both reaction need kind of the acid, okay, so yeah, how do you determine kind of go left or go right, okay, dehydration or hydration, okay. So that's really depend kind of the water amount, okay. So if you use kind of a large amount of water, okay, normally just solvent, okay. So you go kind of the hydration direction, convert alkene to the alcohol, okay. And then if you want to do kind of dehydration reaction, okay, so you can use some kind of drying reagent, okay, to remove any kind of water generated kind of in the reaction, okay, and then push the equipment to the left, okay. So that's just a little bit keep in mind, this reaction kind of somehow kind of reversible reaction, okay. Right, and then mechanism, okay. So still this reaction, follow kind of the original chemistry still follow kind of the Markov-Nikolov rule, okay. So just show you guys one example, okay. All right, so we have this kind of unsymmetrical alkene, okay. All right, so the acid catalyzed hydration reaction also follow kind of Markov-Nikolov rule, okay. So OH goes kind of internal carbon, okay, this carbon. Hydrogen goes kind of terminal carbon with more hydrogen attached, okay. And the reason for that kind of very similar case, so we generate kind of more stable carbon cation, okay. So if hydrogen goes kind of terminal carbon first, okay, and then generate kind of second carbon cation, okay, that's the more stable, okay. And the mechanism I already showed you guys here, okay. So just keep in mind, okay. So eventually you need to remove proton from kind of water, okay. So you kind of find the product, okay. Quite often happen kind of students stop at here, okay. Then kind of we call kind of the hydronium, okay. So that's no down reaction, okay. So you have to kind of push it a little bit forward, okay. All right, and then stereochemistry, okay. Stereochemistry, okay, similar, okay. And so you generate kind of both R and S, okay. So both the enantiomers, okay, because kind of carbon cation, okay. So nucleophile attack from bottom or from the top, okay. And then the drawback of this reaction, okay. So that's at least here, okay. Right, first issue, okay. So we already know that kind of all reaction involve carbon cation, okay. So you can have kind of rearrangement, okay. Kind of two drawback, okay. One to alkyl shift, one to hydride shift, okay. So that's maybe show you guys one example, okay. So we have this alkene try to do kind of the addition reactions, okay, and then theoretically speaking, kind of OH go here, and then hydrogen goes to terminal carbon, okay, but the reality, okay, because you generate kind of second carbon cation next kind of tertiary carbon, okay, so you can have 1,2 hydride shift, okay, eventually real product, okay, like this, okay. So that's rearrangement, okay. And then second problems kind of the low yield, okay. So that's actually already showed here, okay, because this is kind of reversible reactions, okay. And then you can go either directions, okay. So that means kind of hard to get kind of high yield for the kind of the hydration product, okay. So the low yield, okay. And so later we'll learn some kind of other reactions, okay, can also convert kind of alkene to alcohol, okay. So that's kind of give kind of more kind of the higher yield and also the better selectivities, okay. Right. And here we use kind of water as a nucleophile, okay. And actually kind of if you use kind of alcohol as a nucleophile, okay, so normally kind of just use alcohol as solvent, okay. And then you can also add kind of OR group, okay, onto the alcohol, okay, onto the alkene, you generate kind of ether, okay. So that's kind of the kind of extension for this reaction, okay. So so this one we call kind of acid catalyzed kind of the alkoxylation, okay. Okay. Right. So just here the pretty much what happened kind of yeah you have alkene, and then instead of the water, okay, so you use alcohol, okay, so yeah, and then acid at catalyst, okay. All right, so once the reaction is done, okay, so yeah, you generate kind of we then this carbon pick up the hydrogen, and then another carbon pick up the OR group, okay. All right, so you generate ether, okay, and then give you guys quickly one example, okay. Right, so this reaction, this alkene reactor is kind of methanol, okay, and then for example, we use kind of sulfuric acid as catalyst, okay, and then once reaction is done, okay, so we just kind of this ether as kind of final product, okay, so the hydrogen goes kind of terminal carbon for the kind of Markov-Nikolov, okay. Okay, so that's the mechanism one, okay. So just keep in mind, okay, we generate kind of carbon cation as intermediate, okay. And do you guys recall the last year? Okay, cool. Right, so now we move to a little bit harder reactions, okay, harder mechanism, okay. Mechanism two, okay. So this one, okay, so yeah, electrophilic addition to the alkene will some kind of three-membered ring, okay, so yeah. Right. And then for the general, the mechanism actually showed on the screen, okay, but I also want to draw it here, okay. So what happened kind of you have kind of the alkene, okay, and then react with some kind of electron file, okay. So this electron file, okay, so it's also all those kind of pouring electrons, okay. So kind of electron file normally kind of has a negative charge, okay. And then but this electron file also has kind of some lone pair electrons, okay. Lone pair electrons, okay. Right, and then that's happened kind of this the C bond open, okay. So so for example, go this way, okay. Right, and then once it's open, okay, so there kind of pulling electron on this carbon, okay, and then lone pair electrons on this the electron file, okay, can go here, okay, attack this carbon, okay, and eventually you generate kind of some kind of three-membered ring, okay. Positive charge still on the kind of this electron file, okay. So that's different from the mechanism one. Mechanism one is generate kind of the carbon cation. This one generate kind of this three-membered kind of positive charge kind of species, okay. Right, and then the nucleophile come in, okay. Right. So nucleophile, okay, so where to talk, okay, so that's I will explain later, okay, so there kind of some residual chemistry, okay, but here just assuming a talk kind of right carbon, okay. And then nucleophile goes here, okay, negative charge, okay. So that's the overall reaction, okay. And from this reaction, actually kind of some of you, okay, so some questions. See the back to additional highlight. So this one, okay, so mechanism three, okay, mechanism three, okay, so what's the additional species? I will explain this later, okay, so that's has nothing to do with kind of the addition of the hydrogen halide or kind of additional water, okay, so so what species add in, okay, so we'll explain it later, okay, so. Right, so if I draw like this, okay, some of you maybe already noticed, okay, so mechanism two, okay, it's kind of stereochemistry should be kind of anti-addition, okay. So that's the difference from kind of mechanism one, okay. Mechanism one, okay, so you generate kind of the both anti-syn addition product. Mechanism only anti-addition, okay. Right. That's something keep in mind, okay. All right, okay. So now, we'll study kind of what's the species we add kind of kind of CC bond, okay. So under the mechanism two, okay. First one, okay, addition of hydrogen, okay. So I just use kind of X2, okay, as example, okay, hydrogen, okay. Right, so just keep in mind, okay, so this hydrogen has to be kind of bromide or kind of chloride, okay, bromine or chlorine, okay. Right. So no kind of fluorine or kind of iodine, okay. So reason for that kind of fluorine kind of too reactive, okay. So normally, not only you add kind of a pair of the F onto kind of theta bond, okay, so you cause some kind of other oxidation reaction, okay. And then for the iodine, another extreme, okay, so kind of the too inactive, okay, inreactive, okay, or unreactive, okay, maybe unreactive, okay. Too unreactive, okay. So that's kind of if you really want to add kind of iodine onto kind of theta bond, you have to add some kind of other reagent, okay. So the push reaction, okay. So go through kind of other pathway, okay. All right, okay. So that's something in mind, okay. And then now we can study kind of the addition kind of the chloride or bromine, okay. All right. So mechanism actually already showed here, okay. So addition of bromine, okay. So little bit complicated. I want to also draw it here. Okay, so so you guys can have some little bit idea what's going on. Okay. Right, so that's the theta bond. Okay, and then you have bromine. Okay, so for this bromine case, so we draw the all lone pairs. Okay, for the bromine. Okay. All right. Okay, so what happened? Kind of the theta bond kind of opened. Okay. And attack kind of the bromine here, okay. And then meanwhile, okay, so the lone pair electrons on the bromine, okay, attack this carbon, okay, and eventually, okay, so the shared electron between kind of two bromine kind of the atoms, okay, all just break up, okay, give you kind of the bromine, okay. So so that's these two pi bond electrons build up kind of the one the triangle kind of bond, and then they see lone pair electrons on the bromine, okay, build up another bond, okay, and then eventually, okay, so you generate kind of somehow kind of this we call kind of bromium kind of the triangle, okay. So bromine now only has kind of two lone pair electrons, okay, and positive charge, okay, and then you generate kind of the bromide kind of R9. Okay, so that's the first step, okay. All right, and then second step, okay, so the bromide, okay, will attack here from the back of this triangle, okay, so this guy, okay, and then open kind of this triangle, okay, and you generate kind of dibromide, okay. So that's the whole process, okay. Okay, and so intermediate case, so that's called kind of bromium kind of ion, okay. Right, so this reaction actually kind of pretty useful for test kind of alkene, okay. So because the bromine, okay, so bromine is kind of the little bit kind of orange color, okay, orange color, okay. And so if there's no alkene, okay, so you just kind of regular kind of the kind of hydrocarbons, okay, so there's no change of color, okay, so you just kind of see kind of the orange, okay. But if there are kind of the theta bond in the kind of the testing reagent, okay, the testing kind of the substrate, okay, and then the generate kind of the dibromide, okay, dibromide are kind of colorless, okay, no color, okay. So in this case, if you add some kind of the bromine into some kind of the testing reagent, testing substrate, okay, so you see kind of the color change, okay, so to colorless, okay, so that's in kind of there's alkene in the molecule, okay, pretty efficient way to do it, okay. So some other question. So there are kind of regional selectivity, okay. So but that's I will talk about later, okay. So anti-addition, okay. So that's first thing we need to talk about, okay. So regional, mechanism kind of use dihalide and also some other substrate, okay. So I explain, okay. So the first reaction, okay. So under mechanism 1, okay, adding of kind of dihalide, okay. We call it kind of halogen actually kind of generate kind of dihalide, okay. So that's the first reaction under mechanism 2, okay. So there are kind of another 2, okay. Also under mechanism 2, we add other species, okay. All right, so that's kind of the first thing case with the about the stereochemistry case, so anti-addition case. Regiochemistry case, don't worry case, so we talk about later case. Yeah. All right, anti-addition case. So in this case, okay, so yeah. So if we add some kind of the CC bond on kind of add some kind of bromine or kind of chlorine to CC bond, okay. So depends on what's kind of the starting material case, so of the stereochemistry of the alkene, okay. So kind of kind of specific kind of the product, okay. So here's kind of important thing, okay. So you guys need to draw together with me, okay. Right. So for example, okay, I have kind of this cis alkene, okay. C3, okay. All right, and then we try to add kind of the bromine on it, okay. So yeah, Br2, okay. Okay, so the first step, okay, kind of the bromine kind of triangle, okay. So that's pretty easy, okay. So I ignore kind of the lone pair electrons, okay. All right, so that's the intermediate, okay. All right, and then next kind of that's CH3, okay. CH3, okay. Right, next kind of the Br minus coming, okay. Right. So for this one, there's kind of no steric selectivity, okay, no radial selectivity because they have these two kind of carbon, same thing, okay. So can go either from left, okay, open ring like this, or kind of from right, okay. Open ring like this, okay. So in this case, you can have kind of two possible products, okay. Right, so one the black one, okay, so you just kind of some product like this, okay. Actually, draw kind of wedge bond, okay. That's here the somehow kind of the show you real stereochemistry, okay. C3 and then Br, okay. Br, okay, and then H. C3, okay. So that's from the black kind of the attack kind of the right carbon, okay. So if you attack kind of last carbon, okay, so you generate kind of the actually this one should be this one should kind of the red one, okay. So attack kind of last carbon, okay. So attack the right carbon should like this, okay. Product, okay. And then H C3 H and C3, okay. All right, and if you then R and S, okay, so you find kind of see, okay, so the top one, okay, so this one should be S, and then this one should be also S, and then this R, okay. So you find kind of we generate kind of a pair of enantiomer, okay. So the relationship between these two kind of enantiomer, okay. Okay. All right, and then let's try also draw the transport product, okay, for the addition of the bromine, okay. All right, similar thing, okay, we generate kind of some kind of the intermediate kind of triangle, okay. And actually kind of here we can actually start at kind of the dash bond and also wedge bond, okay. Yeah, that's either wedge here and dash here. Yeah. All right, okay, and then next kind of the bromide coming, okay. All right, can either attack here, open the triangle like this way, or attack here this one, open the triangle like this way, okay. All right, so looks like here you also generate a pair of the compound, okay. So let's try to draw the black one, okay. hydrogen, okay, C3, okay. Right, and then for the red one, okay, so yeah, same thing, okay. All right, so afterwards, okay, so yeah, looks like here we generate another pair of enantiomer, okay, and if you design R and S, okay, so you find kind of here this one should be R, S, okay, and then here should be S and then R, okay. All right, but here reality case, so reality case, so if you take a second look, okay, so you find kind of here these two compounds actually kind of same compound, okay, same compound, okay. So yeah, because if you rotate this center kind of central kind of carbon bond on 180 degrees, okay, you rotate this kind of bromide going up, okay, and then Cl point towards you, and then hydrogen kind of CH3 point towards you, okay, and then hydrogen point away from you, okay, and you find kind of symmetry plane, okay. So actually kind of these pairs kind of same compound, and then and you might remember kind of with our kind of special name for this kind of compound, okay. So there are still center in the molecule, but the whole molecule is achiral, okay. So what's kind of compound this is? And then remember, okay. So the whole molecule kind of achiral, but there are kind of still center in the molecule, okay. That's right, okay. Meso compound, okay. Actually, kind of regional meso compound, okay. So that's the kind of tricky thing and also most difficult kind of the part for this chapter, okay. So yeah, label the trans, okay. So about kind of stereochemistry of the mechanism 2, okay. Mechanism 1 is pretty easy, okay. So generate kind of all the possible products, okay. And so yes, this kind of a pair of enantiomer, okay. For mechanism 2, okay, so yeah, because kind of anti-addition, okay. So really depends what's the starting material, okay, and then you can generate kind of a pair of enantiomer or kind of just kind of same compound, the meso compound, okay. So make sure you know how to kind of draw the product and analyze that kind of there's kind of relationship, okay. So yeah, later probably quiz 3, okay. So you will see some kind of question, okay. Ask you kind of draw the product, okay. Ask kind of what's relationship with these two products, okay. A pair of enantiomer or kind of a pair of diastereomer or kind of just same compound, okay. All right. Okay, so that's here, okay, and then give you guys kind of, because that's kind of hard part, okay. Give you guys kind of more example, okay. Right. So here I showed you kind of just a symmetrical arcing, okay. Symmetrical arcing kind of two carbon has same attachment, okay. Okay, two carbon has same. But yeah, if it kind of come to an unsymmetrical arcing, okay, so yeah, little bit a different story, okay. All right. So for example, this arcane, okay, that's unsymmetrical. One kind of methyl, another kind of 1, 2, 3, okay, propyl, okay. So yeah. All right, and then yeah, after reaction is done, okay. You generate kind of a pair compound, okay, and okay. So because kind of anti-addition, okay, so one should be kind of wedge, one should be kind of dash, okay. Right, and then if you design RS, okay, so yeah, the one is R, one is S, okay. And so, okay. So let me see, okay, yeah, this one should be R, this should be S, okay, this one should be S, this should be R, okay. And the relationship between these two actually kind of the enantiomers, okay. Okay. So the trans, okay, looks like here the give you pair of enantiomer, okay. How about cis, okay? Right. So we can also quickly kind of draw the cis product, okay. CR, okay. Remember anti-addition, one wedge, one dash, okay. And then yeah, it's possible you can generate kind of another one, okay. So yeah, 1 dash and then 1 kind of yeah wedge, okay. Right, and then if you then RS, okay, so that's here R, and then S, okay, so, and then that's here another pair of enantiomer, okay. Okay, so for the Cs, okay. So that means kind of here for the unsymmetrical arcing, okay. So generally kind of here, no matter this is Cs or kind of here the trans, okay, both generally kind of a pair of here enantiomers, okay. But for the symmetrical one, okay. All right. So trans give kind of here methyl compound, and but here Cs give kind of here the pair of enantiomer, okay. Yeah. So that's here the something here you have to need to be keep in mind, okay. That's hard part, okay. So we really need to use kind of your mechanism and figure out here the what's product and what's their relationship, okay. Right. And here, okay, so just a little bit explain why it's kind of anti-addition, okay. So this is kind of the space fitting kind of model, okay, real close kind of real the molecular structure, okay. So you can see kind of the intermediate, okay. So the bromium kind of intermediate, okay. You see kind of this is the this orange ball is kind of bromine kind of very huge, okay. So totally block kind of the front, the bottom side of this molecule, the triangle, okay. So when nucleophile coming can only come from the top, okay. Open this triangle, okay. Yeah, similar thing shows here, okay. A bromine too big, okay. Block just the front side, okay, and then bromine can only attack from back side, okay. So that's the why is the anti-addition, okay. Right. So that's I just mentioned, okay. Depends on the configuration of the arcane, okay. So the EOZ cis trans, okay, the stereochemistry kind of the product can be predicted, okay. So it's kind of a pair enantiomer or kind of just kind of methyl compound, okay, or R or S, okay. So that's the some kind of basic the knowledge you have to learn from this chapter, okay. So and also if we do kind of the maximum to kind of addition of bromine to kind of the cyclohexene, okay. So 6 membrane with kind of theta bond inside, okay. And so you can have kind of the anti-addition product, okay, first, okay. So we just kind of trans-diaxial product, and then because kind of these two kind of this one kind of no stable, quickly kind of the kind of do reflip, okay, kind of the di-equatorial kind of per product, okay. All right. So for radiochemistry, I will talk about the next time, okay. So because it's already the 52, okay. Right. Okay. So do you guys have any questions? So the last part kind of most difficult, okay. So